All right, so let us start and welcome. Our guest today is Markus Deserno from Carnegie Mellon University in Pittsburgh. Markus received his PhD from Max Planck Institute for Polymer Physics. And after that, he spent 3 years as a postdoc in the University of California in Los Angeles. After that, he returned to Mainz, to Max Planck Institute, where he acted as a research leader. And since 2007, he is a professor at Carnegie Mellon. So Markus is working in biophysics, and in particular, he is interested in such fundamental blocks of life as membranes, biophysical membranes, biological membranes, proteins, RNA, DNA, and so on. Well, interesting. So some of the methods that he uses are methods of statistical physics, but a particular method which was of interest for me is differential geometries. It's the standard tool of general relativity. So if you're a freshman in general relativity, I suggest you to search for Markus lectures online. So it's a pretty good introduction. So for his research, Markus received different honors, including the Thomas Thomson Award of the Biophysical Society and Otto Ahn Medal of the Max Planck Society. So without further ado, I pass the word to Markus. Thank you very much for accepting the invitation. The word is yours.
All right. Thank you very much. Dimitri, I would like, okay, as I feared, things would go wrong the moment I try it again. Give me 1 second. I'd like to share the screen, but the keynote lecture just closed the last time I opened it. There we go. Here we go again. And now we go to
sure, take your time.
We go to screen share. I predicted this. Here we go. Click, click, and click. Great. Can you see my screen?
Yes, your full screen now. We can see your mouse also.
Perfect. Wonderful. Okay, so let me start now. Thank you very much, Dimitri, for inviting me. It's a great honor to have the opportunity to tell you folks a little bit about the research that we've been doing in my group over the past couple of years. I almost like to say it's wonderful to be with you, but of course I'm not really literally with you. I'm with you by the magic of Zoom. But I Googled, and it turns out that if I were with you, I would be at an amazingly wonderful place. It must be an exceptionally nice place where you are, just in a beautiful city right at the ocean. And one of these days I might make it there, but it's not today. But speaking of maps and landscapes right now, so I'm going to be talking about membranes, and membranes is an incredibly broad landscape over which there is an enormous variety of interesting problems that you can study as an experimentalist, as a physicist, as a simulator. And over these huge landscapes of membranes, I have in fact trodden quite a bit. And so it was almost difficult to figure out, if I have, let's say, the time available for colloquium, what will I talk about? And so I decided to basically talk about two things. The first is a little bit of a review about what continuum theory of membranes generally can tell you about the matter of mediated interactions. And the second shorter story that I will tell you is about how much more recent work on recognizing that certain symmetries in membranes are broken, what that implies to some of the properties of membranes. Okay, so let's get going. Why do I even work on the things that I work on? I work on these things because I'm interested in objects such as these cells. What you see here is a typical image that you might find when you open a typical book on molecular cell biology, or if you just Google on the internet cell, and you would find pictures such as this. And if you look for a while, you realize that almost everything you see in these images are membranes. So typical cell is essentially all membranes. And the reason why that's true is sort of for the same reason that a stereotypical view of a chemistry lab is a room that's completely full of bottles and beakers and test tubes and vials and flasks, because that's what chemists keep their chemicals, right? And so membrane compartments is where cells keep their chemistry and where they do their biochemistry. And admittedly, this particular artist was a little bit too focused on membranes, so it's not quite as bad as this. There is DNA in cells, and there's other things in cells as well. Also, if you look at this image, it looks kind of a little bit suspiciously empty, and that's of course a lie. That's not really going on in real life. In real life, membranes are absolutely chock full of stuff. There's not a single, cubic nanometer in a cell that's not somehow taken up by an important chemical or protein or enzyme or something like this. And that can be much more nicely seen in these illustrations, which are these fantastic images drawn by David Goodsell, that if you haven't seen them before, I highly, highly encourage you to look at these things, because they A, give you a sense of scale, and B, a good sense of crowding of what's really going on inside these living systems. But as nice as these images are, they also lie to you because they look pretty static. In truth, this is a lie as well, because inside cells, many things are completely dynamic. And the best way I've found I could maybe illustrate this for the purpose of today is to show you this amazing multispectral lattice light sheet movie that comes out of the group of Jennifer Lippincott-Schwartz, that shows the dynamics inside a living cell over the course of a few minutes. And what you see here is like 6 different colors, and these 6 different colors label 6 different membrane compartments. For instance, the green bits and pieces are mitochondria, the powerhouse of the cell. This kind of hazy, kind of yellow stuff that seems to be permeating the entire cell is the endoplasmic reticulum. The pinkish thing in the middle is the Golgi apparatus, and there's all kinds of other various types of membrane compartments inside cells. And they're all very dynamic. They not just move around and wiggle around, they also change their connectivity, they split, they merge together. And this is going on constantly, millionfold inside cells. Clearly, looking at something like this with the eyes of a physicist, you're mostly just terrified how extremely complicated all of that is. But I mean, we're interested in this. We would like to understand it. But I mean, all that being said, clearly, as physicists, we cannot headfirst dive into so much complexity and try to understand all of that in one go. We must simplify. We must start with something simpler. And of course, that's what we do. That's how we train, how we think about things. But of course, then the danger is always the worry, well, will it be useful? If can I model a cell as a harmonic oscillator? Will anybody care? And the answer is, if you do it right, they will care. There's enormous amount of really cool stuff you can learn that biologists will be really interested in if you do it well. So looking at something like a membrane such as this is now a zoomed in version. You again see it's a complicated object. It looks like a mattress with springs in it. The springs are proteins. There seem to be hair growing on this thing. These are sugar entities or connections to cytoskeletal elements. For now, all I really would like to care about is the material that makes the membrane itself, which is these objects which are called lipid molecules. And all we need to know about those is that they have like a head group up here, which consists of some kind of chemical moiety that's soluble in water, such as alcohols, sugars, and 2 hydrophobic tails, which is basically oil, fatty acids that do not like to dissolve in water. And if you take a lot of these lipids and throw them together, because of the schizophrenic nature of that half of the molecule likes water and the other half doesn't, what happens is that these molecules aggregate in various kinds of ways to form structures where the non-soluble part of the molecule is kind of tucked away on the inside. And given what the shape of this lipid molecule is, you might get like 0-dimensional aggregate, like little spheres. You get 1-dimensional aggregate, worm-like aggregates, and you get 2-dimensional aggregates such as membranes. There's a whole spectrum from what's called micelles all the way to membranes that happen in this process. What's interesting about this is that you started off with a molecule, something that has a size of maybe 2 nanometers, and at the end of this aggregation process, you arrive at entities that are many microns big. So you scaled up by 3 or 4 orders of magnitude. And this scaling up process brings you from the realm of chemistry to the realm of physics. And the process that gets you there is self-assembly. It's a very well understood process for which there's beautiful statistical physics and thermodynamic theory. And you can predict the size distribution functions of the aggregate, when it happens, et cetera, et cetera. And for us right now, it's sort of the magic pixie dust that lets us forget chemistry. Because once we are at the level of these emergent aggregate, we are perfectly justified to write physical theories for these aggregates while kind of ignoring the underlying microscopic reasons for why they came about in the first place. A common thing in physics that happens when you have scale separation and emergence. And the kind of physics that we now tend to use to describe these larger scale aggregates is continuum elasticity theory. Now, looking at these membranes, you can therefore just say, for the sake of how I would like to treat them, I think these are just surfaces. These surfaces have a particular geometry. There might be fields defined on the surface, which could be lipid concentrations, a lipid species. and there could be charge densities, there could be stress distributions, and all of this just lives happily on a surface. Of course, at this high level of simplification, you could also do molecular dynamic simulations of highly simplified objects, or if all else breaks, you can still try to do some atomistic simulations of such a membrane. All of these things, to some extent, we have done. For today, I will mostly focus on the idea a membrane is a surface with a little bit of coarse-grained modeling in between, basically no words about atomistic simulations. So since we're talking elasticity, let's get all on the same page and figure out what I mean by that. If you take a membrane, how could you deform it? Well, the easiest thing you can do is you can take it and kind of move it sideways, get some gradient of deformation. Something like that would be called shear. You could also take a membrane and just make it bigger, and so you just stretch it. And a third thing you could do, you can take a membrane and curve it into the three-dimensional embedding space. Something like this is called bending. Among these kind of deformations, how do we account for those in an elastic theory for a membrane? Well, the easiest one is the first one, shear, because membranes are fluid and shearing really doesn't cost any energy, so you don't have to account for this. And I should say a static shear doesn't matter. Of course, if you have a shear rate, then there's energy that's constantly being dissipated, and that you have to account for, but only if you do dynamics. From an equilibrium point of view, shear in the membrane plane is irrelevant. Stretch, on the other hand, very much is relevant. In fact, it is so expensive that it also doesn't make much sense to account for it in many situations, because it's extremely expensive to change the area of a membrane by even just a few percent. And so the easiest way to deal with stretch is to say it doesn't happen. The membrane basically keeps its area constant. Bend, on the other hand, is very important, and it's very easy to do. So that's the key soft mode that you have to describe when you wonder about membrane geometry. And I encourage you to think about this in much the same way as what would happen with paper. Paper is also hard to stretch and easy to bend. I would have to, since stretch and bend have different dimensions, there's a lot more that would have to technically be said about exactly what we mean, hard compared to what. But for now, just take it that if you take that basically none of you would be able to take just a piece of paper and stretch it by more than like 1%. But of course, every one of you can just very, very easily bend paper. In that sense, membranes are exactly of the same type. So bending is the thing we need to understand. And bending is described by a bending modulus kappa, about which I'll say a little bit more in the next few slides. For now, let's just say kappa is a modulus that quantifies the extent how expensive it is to bend a membrane. Its units happen to be energy, and you can write it by looking at books such as this in terms of an underlying microscopic theory that expresses a bending modulus in terms of, let's say, a Young's modulus of the material that you're bending and the thickness of the sheet that you're bending. The reason why I'm pointing this out here is because there's an interesting piece of numerical math I can do here by saying, well, what's roughly the value of the bending modulus? What would I, even if knowing nothing, what would I guess about the value of the bending modulus? And just biologically, a good value for it to be is a few tens of kT, let's say 20 kT or something like this. Why do I just randomly come up with that number? Well, that number is interesting for multiple reasons. First of all, it's a sizable amount bigger than thermal energy. And that's important because you don't want thermal fluctuations to kind of fluctuate a membrane into bits and pieces right from the start. At the same time, it is not hugely bigger than thermal energy, and that's important because cells constantly have to deform membrane with the biochemically available energies. You can make these things super rigid. The second thing is that 20 kT is in fact the almost universally available energy scale inside cells. That's not a fluctuation. It's basically the energy that's available from ATP hydrolysis under physiological conditions. And it actually turns out that 20 kT is very close to the bending modulus of many, many membranes. So that's kind of the number that makes a lot of sense. If we now combine this with the structural knowledge that membranes are like 2 molecules thick, maybe 5 nanometers in thickness, then you can combine all these numbers to figure out what the Young modulus of a membrane has to be. And you figure out it's about 10 to the 7 Pascal. Now, I assume most of you don't spend the day in, day out to figure out what Young moduli, so you wouldn't quite know what 10 to the 7 Pascal means. So let me tell you, 10 to the 7 Pascal is about soft rubber. And that's interesting because it tells you that these structural components in these living systems are basically soft matter. And there's a deeper reason for this, and it almost has to be like that, because if I were to decide to make membranes out of the kind of materials that humans use for engineering, steel, concrete, ceramics, stuff with young moduli of 10 to the 10 or 10 to the 11 Pascal, and if you still want this beautiful energy match sort of between thermal and too strong, you would realize that such objects, such steel membranes would have to be a single atom layer thick, and it's very hard to imagine how to do this while getting self-healing stable structures. So the fact that like life is living soft matter is almost necessarily so. Now, having talked about the bending modulus, it's maybe now time to say a little bit about in what kind of physical theory it actually arises. The point about continuum elastic energy is that we can write down a Hamiltonian that describes the membrane's energy as a geometric Hamiltonian that penalizes curvature. And I bolded the words energy and geometric here for a reason, because I wanted to point out that this is in fact one of these amazingly beautiful physical theories where geometry basically sets the entire physics. This is a geometric theory. And the Hamiltonian is a functional of the shape of the membrane. It's an integral over the surface of that shape of some energy density that I still have to explain. Notice that the surface is curved, so whatever parameterization you use, you will have to add a Jacobian because things are invariably curvilinear. And the energy density that you now integrate over is typically something like that. There's three terms, and the only simple term is the first one, sigma. Sigma is a constant, and it's called the surface tension. So you can probably see what this first term basically amounts to is a constant sigma times the total area of the membrane. And this sigma times area is sort of the two-dimensional equivalent of a pressure times volume term in 3 dimensions. So we kind of understand why something like this would be there. The other two terms are geometric, and they involve geometric constants k and r that I have to define. To do so, I remind you that if you have a smooth curved surface, at every point it's kind of funnily curved, and the curvature depends on the direction that you take. And it turns out that there's two directions that are called principal directions, which happen to be orthogonal, along which the radii of curvature are extremal. Their inverses are called principal curvatures, and you can construct geometric invariants out of these principal curvatures. One you can construct is the total curvature k, which is the sum of the principal curvatures, and another one is the Gaussian curvature, which is the product of these principal curvatures. I've written it as, in fact, 1/2 r, because there's another way to see what that is. It's just the Ricci scalar curvature. If you were to describe your membrane properly in Riemannian differential geometry, and you write a Riemann tensor for your 2D surface, then it's double contractions, the Ricci scalar, and that's the thing we're actually talking about. So these two objects essentially describe the geometry of membrane curvature. Incidentally, among all the geometric objects we talked about right now, in particular the Jacobian and the Gaussian curvature are in fact intrinsic. You do not have to know anything about the embedding of the membrane to define those things. That's the same is not true for the extrinsic curvature k, which does depend on the normal vector. And its term, 1/2 kappa k squared, is in fact very important for membrane geometry. Having said that, by the way, so what we're writing down in this energy density is essentially a theory that's quadratic in curvatures and written by the two invariants, which we can write down, k squared and r. Of course, they have prefactors about which this kind of hand-waving argument will know nothing about, which are elastic moduli. And those you have to either derive by underpinning your entire theory with something more finely resolved, or you just go ahead and measure them in experiment or in simulation. But this is the kind of theory that we're working with. Having said that this is a beautiful geometric theory, I cannot help but point out that this has more than just a passing similarity with another geometric theory that you probably know about, which is general relativity. So let me illustrate this by showing you what the Einstein-Hilbert action for gravity would be. It's again a functional of the shape of space-time. It's of course a 4-dimensional integral because space-time is 4-dimensional, and the Jacobian has a little minus sign in there because special relativity has this minus sign in the Minkowski metric. But the other terms are very similar. So there's a constant in there as well. We don't call it the surface tension, we call it the cosmological constant. And there's a bending term in here, which is the space-time curvature, which is in fact exactly the same term we also have in membranes, except we typically don't write it like this in GR. In GR, this kind of copper bar would be given by the 4th power of the speed of light divided by something like the gravitational constant. Something like this would be the bending modulus of space-time. And if you think of like the speed of light in some fluffy sense being large and the gravitational constant being small, this is in fact a very, very large number. And so space-time is very rigid, which is another way of saying that, you know, gravity is kind of weak. You also realize, okay, there's this constant, which for the longest time we thought was 0, but it isn't. We now figured out that space-time, in fact, does have a negative surface tension, and we call it dark energy, and it's the reason why our universe, why the expansion of our universe is accelerating. You also notice, despite all these analogies, the membrane Hamiltonian does have a curvature term that is extrinsic, which is not part of the usual GR, which is entirely intrinsic. And that's one of the key differences. And in fact, that extrinsic term is important. It's almost always the dominant term in membrane elasticity. And finally, the Einstein-Hilbert action does have a term of the matter that is, you know, sitting in space-time, and that does seem to be missing up here. So the next question I'd like to ask, like, is there matter in membranes? And the answer is yes, absolutely. Proteins, drugs, viruses, all kinds of things that can bind to membranes, you could very well classify as matter in that sense. So here's an example of an extremely well-studied protein called the bar domain, whose very job it is to locally bind to a membrane and pinch it a little bit in order to impose a little bit of curvature. Now, this is curvature that is kind of locally a bending angle over the size of the bar domain of maybe 30 degrees, which is weak by biophysical standards. I guess in GR we would call this huge, but in biophysics this is a weak deformation as opposed to a large deformation in biophysics. If you, for instance, have a spherical viral capsid on the way of being enveloped by a membrane, let's say on the way in to a cell or out of a cell, and then you basically wrap the whole thing at some point, and so you get rise to these very, very large deformations of membranes, which in any sense are far away from whatever linear deformation you would like to describe. So those are objects that do bend membranes. Given that, we now ask, is there gravity in membranes? And again, the answer is yes, except we don't call it gravity, of course. We call it membrane-mediated interactions. And the way that this works is that you say we have a membrane, and there's two chunks of stuff, two objects, two proteins, two viruses, binding to the membrane and locally bending it a little bit. Now, if you notice, for instance, the presence of the right object deforms the membrane in such a way that the way the membrane detaches from the left object is perturbed. If the right object weren't there, the membrane on the left object would just, have this shape. And conversely, if you take the left object away, the membrane of the right object would maybe shape like that. Of course, between those two, neither of these shapes is being taken. Instead, the shape of the membrane is jointly determined by the presence of two objects, and that the shape is determined by, let's say, the separation between these two objects, and the curvature is determined, and so the energy is determined, and so there's an interaction. And one interesting question would be like, so is this interaction an attraction or is it a repulsion? Which way would it go? And that's maybe a good idea to just do a little pop quiz here and figure out, well, what do you guys think? If you just have this this very simple scenario, two axisymmetric curved objects that are bound to a membrane, will they attract or will they repel? Now, there's probably some voting options on Zoom, but I don't want to put you on the spot. I just encourage you to just silently think about it for a minute or two. And while you do so, I would like to point out that this is a highly non-trivial question, even for any other field theory that you know. Like if you didn't know anything about gravity and you've never seen the Einstein-Hilbert action, and then I'll show you the Einstein-Hilbert action and say, would this kind of theory give rise to attraction and repulsion? You couldn't immediately tell, assuming you also never thought about quantum field theory of spin-2 particles. Like, if you don't know any of these things, figuring out whether gravity is attractive or repulsive is not an easy task. And for the same reason, figuring out here whether this is an attraction or repulsion is not an easy task. So I hope you internally got some opinions. So let's see what the answer is. And in order to get the answer, let's start easy and do something which I might call Newtonian membrane gravity, which is to assume that membrane space-time is very weakly perturbed, and so that mathematics becomes easy. In that limit, calculations can actually be done relatively straightforwardly. Weak membrane deformations, you superimpose fields, that Newtonian limit is fine. And in that limit, people have figured out that axisymmetric curved disk with some radii ai and some curvatures ji, which is 1 over some radii of curvature, at a distance r, feel the following interaction potential. So the u of r is proportional For the bending rigidity of the membrane, there are some size factors of the geometry in there. It goes like 1 over the 4th power of their separation. So it's a power law, at least at large distance. Leading order is a 1 over r to the 4. And then the way it couples to the curvature charges, the one things, the j's that actually make the deformation, is basically a j1 squared plus a j2 squared. And since the sign of this is always positive, this is always repulsive. There's a rich history of people deriving these things and getting prefactors wrong and getting the sign wrong. This took a while for us to completely appreciate what it would look like. We now understand it's purely repulsive. Even if you take one of these deformations and flip it upside down, it's still repulsive because the sign of the curvature cancels up in squaring. You might in fact notice that this is a rather weird coupling to the kind of the charges that create the deformation, because you might have expected to see something that's proportional to J1 times J2, but it doesn't look like that. And there's a deeper reason why it doesn't, which I can't go into today, but we understand quite well that this is a rather curious interaction here. Anyways, repulsive. So these things repel. Fine. Puzzlingly, though, experiment seems to disagree on that point. And so to show you an example, so here is an experiment that's already more than 20 years old, where people looked at closed membrane bags. Those are called vesicles. This is one of these bags. And they added particles that stick to these membranes. So here's a micron-sized particle. So the whole thing is tens of microns big. Here's a sketch of what you're supposed to look at this. There's a presumably axisymmetric deformation of an object that binds to the membrane and locally imposes a certain amount of deformation. The way that this actually is done is via some molecular version of Velcro, where you put one part of the Velcro on the particle and the opposite part of the membrane, and then they come and then they stick and they deform. So if you're experimentally capable of doing these things, then you can bind colloidal particles to membranes and curve them. And you can, of course, do this in such a way that the direct interaction of these colloidal particles is, for all intents and purposes, absent. So whatever these particles do to each other, they would now do because they're bound to a membrane. So what would happen? So here's an example of what would happen. So we have a time series of 2 such particles sitting again on some sort of vesicle. In the upper left, you see what I mean by that. So they're sitting at some separation r, which you can monitor over time. And so you make basically a time series of r versus t. And it might look like something like this. So you can bounces around back and forth. And at some point, the particles start to see each other, they snap together, and they stay mostly bound at a given distance that's sort of twice their radii. And so that seems like they actually attract, contrary to what I've just told you. But of course, the situation here is not quite so easy. The membrane isn't flat. The particles deform the membrane rather strongly. So there's several approximations that we early on did that might not hold. So this is roughly around the time where we started to worry about these things ourselves. What happens beyond Newtonian? What happens if I have more than 2 particles? What are the corrections to all these simple things? So we started out by doing simulations on these things, but coarse-grained simplified simulations where we used very simple representations of objects that could bind to membranes and locally curve them a little bit, weakly or very, very strongly. The membranes themselves were made out of very simple-looking lipids like these objects up here, which are simplified representations of objects that actually look like this. And he says, oh my God, this looks so much more complicated than this. How can you get away with that? Well, I might say for once, I think I got the aspect ratio about right. And I did get the difference right between the head is something different than the tails, because the head is hydrophilic, the tails are hydrophobic. This you can account for by cleverly choosing interactions. And if you do so, these 3 bead objects can absolutely happily spontaneously self-assemble into 2-dimensional fluid curvature elastic surfaces. And maybe you shouldn't be all that surprised by this, because as physicists, you understand very well that at these steps of emergence of larger scale aggregates forming, an incredible amount of local detail kind of blends out of the picture, becomes irrelevant in a renormalization group sense. And whether you call this renormalization or effective field theory, we call this coarse graining. It's a way of how to do a simplified description of a system that captures the essence of the physics. And so we've done this for many years, and we're pretty confident that we get the membrane right. And so now the question is, in a situation such as this, if I take a membrane and I throw a whole bunch of these particles on there that would curve the membrane, what would they do? Would they just all repel each other into a nice lattice, or what happens? Well, here's what we found what happens. Well, they do diffuse around because the membrane is fluid, but then they do start to locally come together and make little bags where they all pack together. And because they're curved, these bags tend to be curved, so much so that these bags would even detach off the parent membrane they would come from and make little vesicle bags that kind of diffuse then away on the other side of the membrane. So this is very much not just everything repels. At the same time, of course, it's also just not two particles. So what happens with two particles? We also did that. We did careful studies of two objects that bind to the membrane to a fairly large degree. So let's say 70% of that sphere is sticky and the membrane is wrapped around it all the way to 70%. And then you could ask for axisymmetric situations such as this, what's the force as a function of distance? So that's what this plot shows, the force as a function of distance. Positive forces are a repulsion, negative forces are an attraction. And you see at very close separations and mostly large separations, you do mostly see a repulsion, but there's this weird region at like intermediate distances where very clearly the forces are negative. So these particles would attract, despite what I told you about the repulsion. Turns out that you can also investigate this like theoretically, but that's really, really hard because now in the nonlinear regime of strong deformations, you actually have to numerically solve the partial nonlinear differential equations that determine the membrane shape. So that was a bit of a pain. Well, we bit the bullet and we did it. And so we found interaction curves such as this. Again, this is the force as a function of separation between these objects. You see 4 different symbols or curves that correspond to sort of detachment angles or amounts of curvatures of 3 pi over 8, 4 pi over 8, 5 pi over 8, and 6 pi over 8. Among those 4 simulations, the easiest one qualitatively to understand is 3 pi over 8, which is the weakest kind of deformation, because what you essentially see is a repulsion that becomes stronger as the particles get closer together. And that's sort of what you expect from linear theory. So qualitatively, this is still sort of within our mental theater of expectation, but quantitatively it's off, because this curve is the linear prediction for 3 pi over 8, which gives you a stronger repulsion. So in reality, the repulsion is now weaker than what linear theory would tell you. And if you now go ahead and make the curvature deformation stronger, go from 3 pi over 8 to 4 pi over 8, which means you basically have a hemisphere that's being bound, then you even qualitatively change in the sense that the interaction potential now starts to, as large distances, it starts being repulsive, but then it changes its mind and turns into attraction that seems to persist all the way to distance 0. And so that's very curious. And if you now make the deformation even larger beyond 90 degrees, then it turns out that the trend of repulsion attraction keeps going on, but then at very short distances, this thing again turns back into a repulsion. And so I like to point out that this kind of overall shape for the kind of particles that we had in our simulations is pretty much qualitatively what we find. Repulsion at large distances, an intermediate regime of attraction, and then repulsion again at very short distances. And qualitatively, that's what we find. Quantitatively, there are some important distances, but I would say that through the eyes of love, this is probably a good explanation of what we found in our simulations. I'd also like to point out, just looking at this, remember when I asked you, is it an attraction or is it a repulsion? In this case, the system changed its mind twice. You started out with a repulsion and it says, yeah, in this range are going to be attractive, and then, never mind, it's going to be repulsion again. This is crazier than general relativity. If you take general relativity and you go to the strongly nonlinear regime, is you have 2 neutron stars that you bring closer together, they will attract, right? And always attract. It's not like that there's some magic distance about twice the neutron star radius where that's repel. So that would never happen. GR never changes the sign of the interaction, but these membrane kind of systems do change the sign of interaction, which is bizarre. It's weird. It's one of the quirks of this kind of system. Okay, now, so far everything I talked about is energies, in particular ground state energies. But of course, membranes fluctuate in a thermal environment. And the reason why they fluctuate is because their rigidity is not orders and orders of magnitude larger than the thermal energy, but maybe just 10, 20 times larger than thermal energy. And so as you can see in this movie down there, this is one of these membrane bags, a vesicle that's just sitting there in a bottle of something, water, at room temperature, and it wobbles around, it fluctuates and oscillates. That's what it does. And so a question you could ask, like, okay, so we have these fluctuations. What do they do? How am I supposed to think about these fluctuations? And the clean way to think about this is that, okay, so here we have a membrane. This is one membrane, and it's flat and easy and nice and ground state, because that's what maybe the membrane wants to do in the least deformed case. But the membrane can also fluctuate, and there's many, many ways of how a membrane could be not in its ground state, right? And so if you're poetically inclined, you might maybe remember how this gentleman once started a novel by saying all happy families are alike, but every unhappy family is unhappy in its own way, which I like to translate into physics here, like all the ground states are unique and boring, but the excited states come with multiple degeneracies and are interesting in their own right. And of course, the slightly less poetic version of this is what this gentleman then figured out. Oh, degeneracy, I know what to do with degeneracy. I take the log, and then I call it entropy. And so membrane fluctuations increase the entropy of a system. That's why they happen, and they decrease the free energy of the system. So you would always have to, since everything is free energies, of course, at the end of the day, you would have to account for these fluctuations. And so from an entropic point of view, you want these fluctuations to be there. And that has consequences. And let me quickly walk you through 3 consequences of these fluctuations. The first thing is that if you just have 2 membranes, they're fluctuating, they're at a distance d apart, they will repel. Maybe that's not entirely mysterious because they kind of bounce against each other, and so that seems like a repulsion. But how would we quantify this? Well, it turns out that the potential, the sort of the Gibbs free energy per unit area between these two membranes is something like kT squared divided by the rigidity divided by their distance squared. And that's a rather curious interaction potential if you think about it. It does come from fluctuations, but why would it be proportional to the square of the temperature? And the fact that it goes like 1 over distance squared means this is an extraordinarily long-range interaction. So it's incredibly important in biology because it's much, much larger than anything else that could possibly have much larger than electrostatics in all practical purposes. And I would like to sort of quickly show you how you can reason your way into understanding that it has to look like that. So let me give you an argument that answers this up to the prefactor. The prefactor is difficult, but the scaling form is very easy, and it can be derived very, very elegantly by this argument from the paper of Helfrich and Servos. So the idea is, for the sake of arguments, instead of just looking at 2 membranes, let me just look at a whole stack of membranes that are all fluctuating and sitting on top of each other, every membrane on average separation d from the next one. Under these situations, I could now worry about what's the mean squared fluctuation of a membrane. If I describe membranes by something like u of x and y, what's the mean squared u? And it turns out that there's 2 expressions you could write down. The first one, simply due to confinement. Now, the mean squared fluctuation has to be related to the distance of the particles, and by dimension has to be d squared. So that's not particularly mysterious. If the membrane were unconfined, if there weren't all these other membranes bouncing against, we could also calculate quite easily what the mean squared fluctuation are. It turns out to be kT divided by the bending rigidity times the area of the membrane. I'm not going to show you this, but basically for a quadratic curvature fluctuating theory under weak deformation, this is just basically just equipartition theory. It's extremely easy to find out. Well, what that means is also that as you make a membrane patch larger, its mean squared amplitude becomes larger, and at some point it becomes bigger than the confinement, and then the membrane notices that it's confined, and the without confinement formula has to be wrong. So that tells you that there is a largest A that you could have, like a maximal unconfined patch that would not yet notice that you're part of a stack of membrane rather than a lonely membrane. It's now useful to think of your stack of membranes as every membrane consisting of these patches. The patches individually don't notice the confinement, but in the sense maybe they just only bounce once at the upper and the lower edge. And so you could think of these patches stacked on top of each other as a one-dimensional gas of patches. And there's a force between them, which is then just the ideal gas law, which is kT divided by the separation d. So kT over d is the force between these patches. And the pressure between these patches is that force divided by the area. So the pressure is kT over d divided by a. Putting in what we know about a, it becomes kT squared over kappa d cubed integrating it up will give you the formula that I just said. To do more work, if you want the prefactor, in fact, a lot more work for the precise prefactor, because this is a non-trivial statistical mechanics problem, people have done this, and these interactions are enormously important for the way membranes interact with each other. Now, of course, so membranes repel each other, but a membrane sort of, because it fluctuates, repels almost anything else as well. So if you have some object, a protein, a virus, or whatever it is, of some overall, real estate area A, and you would like to go and bind on the membrane, that's possible if they attract, but then you have to remove fluctuation modes on the membrane. To lowest order argument, the number of modes you lose is proportional to the area divided by some microscopic cutoff distance A squared. And so the entropy loss and the free energy loss of binding is again kT times the log of that area. So this doesn't seem to grow particularly dramatically with A. So you say maybe that's not very important, but the point is not so much how this grows with A, but that for any reasonable A size of a typical protein or something like this, this reduction is a few, maybe 2 or 3 kT. And so it is relevant because most binding energies are not just hundreds of kT, they are in the few kT range. And so the entropic loss of fluctuations for binding is in fact an important player in all kinds of molecules coming to membranes and wanting to bind. And the final example I like to make is if you have now 2 of these objects bound to a membrane, they now paid their individual entropic costs, so that's fine. They each have, let's say, size r, and there are distance little r away, which I can write as some dimensionless number x times their typical size. And so the question is, what happens now? Well, the rest of the membrane can still happily fluctuate, but what you now have to do, if you figure out, if you want to count all the fluctuation modes, you have to solve the mode spectrum of the system subject to boundary conditions that are being imposed by 2 compact objects. And that matters because the joint fluctuation spectrum now does depend on the separation of these 2 particles, because the boundary conditions depend on little r. And so people have worked out what that implies. And what it implies is a fluctuation-driven attraction between these objects, which is pretty universal, because like minus kT times number 6 divided by scaled distance to the power of 4. And there's a rich history, again, of people looking into this, getting prefactors wrong, getting the sign wrong, until finally we agree on what this thing is supposed to look like. You will also notice, or some of you might notice, that this is what I'm describing here is essentially a critical Casimir effect. What we have is a field that would like to fluctuate, and then we put boundary conditions on this field from compact objects, and these confine the fluctuations in a way that depends on their mutual separation. So this originally was discovered in quantum electrodynamics by Casimir, but it arises essentially for any fluctuating field on which you impose boundary conditions. Now, notice, by the way, that the power law 1 over distance to the power of 4 is exactly the same power law that we had for the repulsion between curved objects, except now it's attractive. And so there could be an interesting balance of attraction versus repulsion, depending on which of these 2 effects wins. And notice also that it's a 6 over x to the 4 plus ... because this is, again, just the lowest order expansion for small distances. For large distances, and if you come closer, there's higher order corrections. What are these higher order corrections? Well, for the longest time, people didn't want to calculate them because it's kind of awkward and difficult. And at some point, people kind of worked out if we were to do our calculations, the next term would be 1 over x to the 8, but we can't be bothered doing it because it's just. And in some sense, this is also where we entered the field. I described this problem to a good colleague of mine here at Carnegie Mellon, Ira Rothstein, who is a leading expert in the world of something that's called effective field theory. And he says, oh, wow, this is exactly the kind of problem you would deal with effective field theory by saying, rather than dealing with compact objects and the awkwardness of boundary conditions of compact objects, replace these compact objects by point particles, but then decorate them with a tower of polarizabilities that would account for the effects that otherwise come from finite size. And so we did that, and it turns out with doing this, you can calculate a whole bunch of more orders for this kind of interactions. So we just cranked it to, I don't know, 1 over x to the 20 or so on. And you might say, well, nobody cares about the 1 over x to the 20 term, and that's maybe true. But the point is that the fact that we could crank out all these terms without dying in the process means that the formalism was very, very nice. And I do point out that the next order that we found is not 1 over x to the 8. It's 1 over x to the 6. And there's a deep reason to understand why. because the so far existing theories that would try to understand this were not quite systematic and missed one of the important expansion parameters in the system, essentially the tower of polarizabilities. Great. So this kind of looks like a theoretical toy problem, and it's clearly a very beautiful problem if you like these kind of calculations. But notice that we have now moved to the level of, critical Casimir interactions in idealized surfaces and doing partition functions about all of this. You might very well worry at this moment, do biologists care about this, or have you now clearly moved up into a physicist like happy land where biologists no longer listen? It's not quite true. And the way I would show this is by pointing out to this amazing publication, which came out, I think, 6 years ago, which has an interesting title. It says Mechanism of Sugar Toxin Clustering on Membranes. What does that mean? Well, sugar toxin sounds bad because toxin sounds bad. So if you get sugar toxin in your body, you're in trouble. In fact, sugar toxicosis is a bad thing worldwide. About 1 million people die each year of sugar toxicosis. It's very related to cholera toxin. It's in cholera. It's the kind of disease you get when you get contaminated waters and you get diarrhea and you kind of dehydrate. And if you don't drink enough water, you die. And the way that this mechanically works is that you get these bacteria, the bacteria extrude these toxins, and the toxins get taken up somehow by your cells where they shut off protein productions and you die. But how do they get into the cell? The idea is that they cluster and then make little bubbles and go into the cell, maybe not unlike the movie that I just showed you 15 minutes ago. So you have to explain how they all come together. And these authors, several of which are dyed-in-the-wool biologists, said it is quite possible that the attraction between these particles leading ultimately to take up is driven by membrane fluctuations. And unless you think that I'm making these things up, the very first keyword in their paper is Casimir force. And so I find it rather beautiful that biologists wake up to the idea that these kind of physical concepts might be very, very relevant to biological problems. Great. Okay, so for the last part of my talk, everything that I told you right now so far is a consequence of a membrane being a curvature elastic surface. But it turns out that's not actually what a membrane is. It's two curvature elastic surfaces. Like here they are, number one and number two. Membranes are bilayers. What does this change? Well, often it changes nothing. You can just independently think of bending both of these sheets simultaneously. You just add up the curvature, everything just factor of 2. It's not a big deal unless these two individual sheets are not actually the same. Things get a lot more interesting if these two individual leaflets are not identical. That breaks the up-down symmetry of the membrane. And as you all know, as physicists, once a symmetry is broken, all kinds of amazing stuff can happen. And so that's the last little bit of thing that I'd like to talk about in a few minutes. And this matters because many biomembranes are in fact asymmetric, by which I mean, very generally speaking, that those two sides of a membrane differ in at least one physical property. And that physical property, for the longest time that people have been thinking about and also knowing about, is the lipid composition, the types of lipids that live on one side versus the types of lipids that live on the other side. We know this for mostly 50 years. But there's many other ways in which the two different sides could not be the same. And this is something that created interest in the last couple of years. It was known, and there's a very beautiful recent paper that studied this in very great detail, that how, let's say, the head group type of lipids in something like the human red blood cell membrane is different between the outside and the inside, how the tail saturation, which is physics lingo speak for the order parameter of a lipid, how they might differ, how the number of lipids in the two different sides might differ, or how the charge of lipids might differ. And thinking about these things, the one stuff that we got curious about is it could also be that the tension, the mechanical tension in the two different leaflets on the two different sides could be different. What do I mean by that? Well, imagine building a membrane out of just one type of lipid, so it's about as symmetric as you get it, but then you overcrowd one of the two sides and you leave holes in the other side. Then this side is going to be under compression and this side is under tension, but it's still one membrane. So the way to think about this is that these two leaflets of the membrane are like springs with a rest length, but the rest length is different because the number of lipids in the two leaflets is different. But you want them to be part of the same membrane, so you have to force them to the same length. So you kind of do that kind of forcing, and as a consequence, one of the springs has to stretch and the other string has to compress. But all of this can still happen under condition of zero net force. That would mean if you actually have such a membrane and you were capable of measuring the tension of the entire membrane, which you are, we know experimentally how to do that, it would turn out that the net tension of the membrane might be zero, and you would not realize that the two individual leaflets on their own might be under rather significant stress, because you cannot see this. But that being said, even in this situation, if the force is zero, the torque isn't necessarily zero, and the torque can have consequences. In fact, a membrane that is stress-free but not torque-free would bend. And that is interesting because it brings the problem of lateral stress differences to the whole story of curvature that I talked about so far. So let me illustrate this just at the end with a couple of pictures, right? If you imagine with an incredibly symmetric membrane, the standard way people think about making it asymmetric is to replace one leaflet by a different type of lipid that, by the shape that I'm indicating, would maybe prefer a slightly different curvature. Another thing you could do is you could just overcrowd one of the leaflets. In both cases, the response of the membrane might be to bend, but it's important to realize that that bending happens in different ways and for different reasons. In the upper case, the reason the bending happens is because the membrane would like to reduce its curvature stress, because the lipids really would like to have, the outer lipids in particular, really would like to have a different curvature. And so the membrane bends at the expense of creating lateral stress, because now the outer leaflet needs to stretch and the inner leaflet needs to compress. That's exactly opposite in the other side, where the reason why the membrane bends in the first place is that it would like to relieve these kind of lateral stresses. So it bends, but at the expense of creating curvature stresses that weren't there before. This is interesting because these two different games I could play simultaneously by building membranes that have both kinds of stress problems, if you like, at the same point. So a membrane such as this could bend because the curvature stresses wins, or it could bend because the lateral stresses wins. And looking at pictures such as this, you will notice that these three membranes that all have different shapes have exactly the same composition of lipids on the two different sides. And yet both their shapes and their internal stresses are very different. And that matters because for the longest part, people were just thinking about lipid type as the one and only way how a membrane can be asymmetric. This is very much not the case. And so all of this is a matter of balance. Like a membrane such as this could be perfectly flat, and yet the reason why it's flat is because there's a tug of war between two different torques that have to balance, the torque due to lateral stress and the torque due to curvature. The torque due to lateral stress is relatively easy to figure out. If you have some sort of tension delta sigma that acts in, let's say, the upper leaflet, and it acts at the proper reference point of the upper leaflet, which is a displacement distance z0 away from the midplane of the membrane. Just think about this as the mid surface of this upper leaflet. Then this z0 is like a lever arm, and so the torque is like delta sigma times the lever arm. The torque due to curvature is a little bit harder to motivate because now we have to go into, let's say, the curvature mechanics. So let me just tell you that a membrane that is flat but has a preferred spontaneous curvature Kb would have a torque, which is their bending rigidity times that curvature. Now, this balance has to hold if you have a flat membrane, and so you can solve it for the differential stress. There goes my piece of math for today. And so you can calculate what the differential stress is because all the numbers on the right-hand side we can measure or we know. So I'm throwing in some numbers. A typical rigidity of biomembranes may be 30 kT. A typical spontaneous curvature that is on the weak side, it's maybe like 0.02 inverse nanometer, and that displacement distance, knowing about how big leaflets are, is maybe something like a nanometer. If I put in numbers into this expression, I get a differential stress of about 2.5 millinewtons per meter, which I understand will probably tell you nothing. So I tell you that 2.5 millinewtons per meter is enormous. This is easily 100 times larger than any typical cellular tensions at the bilayer level that people think about. And so this puts stresses on for instance, the proteins that are embedded in membranes that are 2 orders of magnitude larger than anything that people so far have, let's say, studied in molecular dynamics simulations, because it's 2 orders of magnitude larger than anything that matters. People thought it matters. We also showed that one thing that this thing does is it changes the material properties of the entire membrane. So we measured the rigidity of a membrane, that kappa value, as a function of asymmetry, like how do you unbalance the stresses, the lipid packing on the two sides, and we realized that beyond a certain amount of asymmetry, when the stresses become of the order of a few millinewtons per meter, there seems to be something like a transition that gets the membrane into a much stiffer space that is, in our case, for this simplified membrane model, about 50 times stiffer than you would ordinarily think. Clearly, that has massive implications for many, many things that are going on in membranes. So these were the stories I wanted to tell, and we just quickly summarize what take-home messages are that would be nice to remember. Membranes itself, the thing I talked about, are emergent structures made out of lipids via the beautiful process of self-assembly, and they can be treated as entities in their own right, typically fluid curvature elastic surfaces. And the physics that does that comes almost entirely from geometry. There's geometric Hamiltonians describing it, and maybe on top of that, fluctuations. You do statistical physics for geometric field theories. One of the examples I showed you what this thing implies is that both shapes and fluctuations can mediate forces between objects bound to membranes, and that these might be sizable and these might matter in biology. And towards the end, I showed you that if you break the up-down symmetry of these membranes, which for the longest time were just modeled as symmetric, this creates huge hidden forces that you might not see in simple experiment, but whose implications could be large, and we're only just about beginning to understand. So that was my story. Let me end by acknowledging all the amazing people that over the years worked with me to help me understand these things, in particular, the people who were part of the stories that I told today. And with that, I would like to finish and thank you for your attention, and we'll be very happy to answer any questions if you have any. Thank you very much.
Oh, thank you very much, Markus, and let us at least formally thank Markus for his great primer on geometry and fluctuations in biological membranes. So we can now pass to questions, and we have a variety of ways to ask the questions. You can raise your hand in Zoom, or you can write your question in the chat, or if you're following us on YouTube, you can also post your question there. So let me start maybe asking the first question. So for example, in this discussion of the force, which was mediated by the shape of the membrane, the results that you've shown, did you obtain them from the effective theory, from this Helfrich theory, Hamiltonian that you showed us, or is it any simplification?
Both ways. These results were originally derived in the early 90s, definitely not using effective field theory, but just basically brute force trying to solve the shape equation under linearized conditions, where you apply boundary condition on this particle, boundary condition on that particle, make them simultaneously match, do a two-point multiple multipole expansion, match coefficients, and then you get the leading order. And that was, because this is a bit of a messy process, it took a while to get it right. We have indeed also looked at these forces using effective field theory, and then you can add 20 more terms, and they look the way they do. We looked at situations where the particles have different sizes and different curvatures, and one really hard thing was to look at particles that are not axisymmetric, because then all hell breaks loose. You don't just get mediated forces, you get mediated torques. And because of a broken symmetry, certain cancellations that happen at low order don't happen anymore, and you get lower order interactions that weren't there in the axisymmetric case.
I see. So my question is, so if you compare this to general relativity, so one of the first solutions that was obtained for general relativity, people were just Schwarzschild was searching for just a radially symmetric solution, and he found the famous black hole, right? Is there any analog of black hole in the membrane?
I'm not sure about analogs of black holes, but certainly there are analogs of simple solution under axis symmetry. So if I take a sphere and I bind it to a membrane, and if let's say I have a certain fraction of the sphere bound, then that part of the membrane is a sphere, and then the rest of the membrane has a little bit of a shape that looks like this. Under conditions of zero tension, there's an exact solution for the shape, and that's a catenoid. Axisymmetric minimal surface, which in fact has zero curvature energy. It gets the functional down as low as you want. And so the more you wrap the particle, the more you get kind of a catenoidal shape until you can pinch off at the end, and then maybe the pinch off is something like wholly terrible or so on. Things become more complicated in the presence of tension, because then you no longer have exact solutions. You get objects that look like this, and they bend over and they become mostly flat. They don't logarithmically diverge, they become exponentially flat. And again, the more you wrap, the more you go around like okay. I don't know how you think about this in terms of black holes. There are, of course, instabilities you could imagine if the reason why you attach to such a particle is because of some stickiness. There's an energy per unit area of the membrane binding. Then the more sticky you make the membrane, the more it kind of wraps up the particle, until there comes a point where the equilibrium state just 100% jumps all the way to the other end. The particle is completely taken up. There's kind of a snap-through transition where the whole thing sort of collapses and spits out the thing. Again, this is an instability that I don't think is strictly equivalent to a black hole, but there's a lot of really cute stuff you can do with axisymmetric solutions. The moment axisymmetry goes out of the window, it's not quite as hard as two orbiting black holes, but it's you have to unpack a whole lot of different techniques. A fun fact, by the way, in order to understand this, let's say, in spiraling black holes, which is, again, you solve space-time in 4 dimensions around two compact black hole objects, that's a beautiful way you can deal with effective field theory. And in fact, Ira Rothstein, who taught us effective field theory, had done that. And having done that, he said, we can do the same thing on membranes. It's probably just easier, which it was. It's not as hard as the inspiring black hole problem.
Okay, yeah, that was more or less what I was asking about. There's a question from participants from Vera. I don't know if Vera can ask the question herself, or I can read it. So she posted it in the chat. Does charge play any important part in all these processes?
Okay, charge is almost always a difficult question in soft matter physics for a variety of reasons. I could give another talk about how this is a difficult question, but there's various levels of how you can answer the question. One way to answer the question is that in biology, charge typically happens in an environment of some salt concentration. In this environment, interactions are not 1/r. There are 1/r times an exponential screening factor with a Debye length that is typically of the order of 1 nanometer. 1 nanometer is small compared to the thickness of a membrane. So it is typically very small compared to any of the sizes that I talked about today. So from that point of view, you don't worry about charge. But that's only the beginning of the story. Because if you have, for instance, a positive particle binding to a membrane where a certain fraction of lipids is negatively charged, then yes, that would drive binding. It would drive local demixing of these lipids, which has an entropic component. You locally demix the counter ions in the vicinity, which again has an entropic component. So there's all kinds of complications that now show up. And even though the Debye length is short, if you get two objects that are actually very heavily charged, even a short Debye length gives rather sizable perturbations over maybe 10 nanometers away from the object that matter. In order to properly treat this, I've always felt that if you want to do charge right, you have to look at the screening and the counter ions properly and explicitly. That is typically not done when you do coarse-grained simulations. You can do this maybe with colloidal particles, but with membranes, you have the following really awkward problem: is that the interior of a membrane is basically oil, so it has a dielectric constant of 2, and this is embedded in water, which has a dielectric constant of 80. So there's a huge dielectric boundary. This affects the way electric fields propagate in these systems, but it's almost never part of coarse-grained simulations. It's part of atomistic simulations where water is explicit, and so this dielectric boundary happens automatically. In coarse-grained simulations, it rarely happens, and so I tend to be always skeptical of coarse-grained simulations that include electrostatics but don't include dielectric effects of that type. In that case, I would rather just replace charge by some effective attraction. But I guess there's nothing super general you can say about this thing. It depends very much on exactly what the problem is, like what's the easiest kind of treatment you can get away with.
Okay, so we have another question from Gilberto. He's asking if we consider membrane in a fluid, will pressure or viscosity affect the bending?
Yes. Just like I said, there's the surface tension term, which is surface tension times area, which is sort of the equivalent of pressure times volume. But there is a pressure times volume term if you have a closed membrane and there's a pressure on the inside and there's a pressure on the outside. That very much affects what's going on. You could either think of the pressure as like some externally imposed pressure, because let's say your vesicle is, you hold it in a pipette and you suck on the pipette or you spit, so you can control the pressure difference. Or you say, I'm just using the pressure as a Lagrange multiplier to set the volume inside my vesicle, which could be much less than the size of an equi-area sphere. And so the vesicle has to form crumpled shapes. There's a lot of work in the 1990s to figure out what are the equilibrium shapes of membranes that have certain reduced volumes. When you ask viscosity, then the answer says anything relating to viscosity will only matter for dynamics. But of course, there are very important dynamical questions that you care about. Let's say if you think about red blood cells, which are basically like closed membrane bags, they move through your capillaries all the time. And so if you want to understand how that motion and the shear gradient in your capillary affect the shape and the motion of these red blood cells, you have to account for viscosity. Again, people have done so and found that there's beautiful phase diagrams about exactly how these objects move, what shapes they take, whether they tumble around, whether they rotate, whether they change shape in a symmetric way, whether they flip-flop, something like this. There's a lot of research on the motion of objects such as red blood cells and the shear flow, and it affects the shape. I don't think it affects the bending rigidity as such, but there's a very nice feedback mechanism of the dynamics and the shape of these vesicles.
Okay, so let's see if there's any follow-up. I have another question about things you talked. So there were two kind of mechanisms for forces that you discussed. So one due to shapes and the other one due to fluctuations. So is there any relation between them?
Not directly, because those are really independent pieces of physics. As you can sort of see by their functional form, the forces that come from sort of the ground state are proportional to the bending rigidity, so the properties of the membrane. The forces due to fluctuations are completely independent of the bending rigidity. And so to some extent, you could tune their relative strength. By the way, the forces due to the ground state are proportional to the bending rigidity and the curvature imprint. So if you make the curvature imprint 0, you just take flat disks, then the ground state forces are gone. And if you now just start to curve them a little bit, the ground state forces become larger and larger, and at some point they might compete against the attractive forces. And so you can tune this to become an interesting balance. Since kappa is a relatively large number, the repulsion very quickly becomes an important player compared to the KT attraction. But that really just is a matter of protein shape.
The reason why I asked this because you showed this paper, right, that cited the Casimir force as the origin, for example, of the Shiga toxins, right, that you talked about. So how do you know that this is due to Casimir force or due to?
I don't know this. I have talked to the authors and says, what makes you think it's Casimir? And they said, well, we measured various things and we ruled out certain other reasons. And so at some point, we just can't think of anything else that's out there that will give rise to an attraction. And Casimir is right there to give rise to a large long-range attraction. I would have to reread the paper again, precisely what the argument was. But part of it is really that all the other interactions that you could think about are repulsive. And Casimir is like this. It's a little bit like, Casimir interactions and fluctuation-mediated interaction have a little bit of a smell of van der Waals. And so in ordinary, soft matter physics, when things attract, one of the first culprits is just a van der Waals attraction. So I guess in that sense, you would make that argument. In order to, and this is a paper written for chemists, by biologists. If that were a paper written for physicists, you would like to see a whole lot more testing and universality class, arguments about why you think it's Casimir. And they, for obvious reasons, haven't done this because it's difficult to do these experiments. But I encourage people who are curious about this to go into the field and start to think about this. There's amazing stuff going on. You don't have to do Casimir forces, critical Casimir, just with complicated critical mixtures or liquid helium and stuff like this. You can just do this with membranes. We know it's there. You just have to find a way to make it visible.
There's also some, I read about, well, my knowledge is basically on Wikipedia level, is importance aggregation of proteins, for example, membranes. Once, for example, maybe a related thing is called lipid rafts, right? Which are said to play an important role. So is it somehow, what's the relation with the forces and discussion of your lecture today?
There is a relation. First of all, what a lipid raft is depends quite on who you asked. That story hasn't been settled. One notion of a lipid raft that I like is a story that relates lipid rafts to phase coexistence in membranes by saying, well, membranes are not just one type of lipid. There are mixtures of lipid, and because they're mixtures, there could be different phases. In particular, there is a phase coexistence in very canonical ternary mixtures of, let's say, fairly ordered lipids, fairly disordered lipids, plus cholesterol as a third component, where you can have coexistence between two different phases, what's called a liquid ordered and a liquid disordered phase. Both of those are fluid phases, but they differ in some sort of lipid order parameter. And it even turns out, because they're both fluid phases, that at some point when they become similar, there's a critical point. And so at that critical point, you get very long range fluctuations of phase type. You just think about it like an Ising model at a critical point. In fact, it's exactly like an Ising model at a critical point, because if you count order parameter and dimensionality, it's an Ising model, and people have argued, work by Sarah Veach and colleagues have shown that this is essentially 2D Ising critical thermodynamics. Now, if you have a membrane that is close to such a critical point, it has these large-scale compositional fluctuations of like phase A, phase B, and you have proteins that preferentially solvate in one of the two phases, then you get mediated attractions between these two proteins, not by the shape of the membrane, but by these critical fluctuations. It's in some sense a protein that likes phase A, surrounds itself by a halo of A. There's another protein that also has a halo of A, and these halos of A could now again overlap and mediate an interaction. If you go through the math for that part, it turns out that's an attraction. And this attraction can be fairly long range because these critical fluctuations can be very, very long range. And so one of the ideas, that idea is sort of spearheaded again by Sarah Veach, is that cellular membranes might be, well, you can experimentally check them, are tuned to such an extent that the composition is essentially critical, but the temperature is maybe 15 to 20 degrees above the critical point, so that these critical fluctuations have zoomed down to length scales that are maybe only 20, 30, 40 nanometers, which is the size that people believe these rafts to have. So it's again a mediated interaction problem, but it's not driven by geometry, it's driven by composition.
Okay, well, thank you very much. I don't see any further questions. I hope that our participants were convinced that there's a lot of interest in physics and this complex systems like membranes. And well, I thank you again, Markus, for giving this great talk, for accepting the invitation.
Thank you.
And we'll see you all again in a week with more seminars.
Thank you. Bye-bye, everyone.
Bye. Take care.